Alright, the first are two videos about aromatic hydrocarbons. Aromatic hydrocarbons are based around this molecule called benzene. And it's got the molecular formula C6H6. How did they come up with this formula C6H6? They did it just as you used to do it in grade 11 chemistry when you did find the molecular formula, or kind of like find the empirical formula. Their questions were, your answers started off with assume a 100-gram sample and blah blah blah, and you had so much percentage of carbon, so much hydrogen. You turn it to moles, you divide, and so on and so forth. But while they knew this was the formula, they were not sure what its structure was, and it took from 1825 all the way up to 1931 before they finally figured it out. Here are some ideas. I could have a ring of 6 with alternating double bonds. I could have two rings kind of attached together with a double bond here. That one works. I could have a string here, or a line of them with two triple bonds somewhere in there. That will work, and there's different positions for these that work. I could have a ring of 5 with a double bond carbon sticking off the edge. There's another one with a ring of, or sorry, not a ring, a straight line of 6, and in there you need two double bonds and a triple bond. That one will work. But they were never sure which one was right. Now, the correct structure will only undergo a substitution reaction. Organic chemists don't really like to use the types of reactions, those names that you learned in grade 11 or in grade 9 or 10. They use some different terms for them. One of the terms they use is substitution reaction. So in a substitution reaction, something goes out, something comes out, and something goes in. So for example, if this was to undergo a substitution reaction, this hydrogen might come out and a fluorine or something might come in. That's a substitution reaction. An addition reaction is when you've got a molecule like this, and then you add in something like water or bromine gas or chlorine gas, and what happens is that you only have one product in the end. Two things seem to be coming together to make one. And to do that, I wrote here, you need a double bond. I hope you all realize that the only way you're adding this to this and making everybody happy is if one of these bonds breaks, and then I can give something to this carbon and something to this carbon to make them happy. But these things, benzene itself never wanted to add in, only wanted to substitute. One thing out, one thing in. Now, it only undergoes one monosubstitution reaction product. So if I take a hydrogen out, it doesn't matter which of the 6 hydrogens I take out, I'm only going to get one product. So for example, let's take a look at this molecule right here. If I take out this hydrogen and replace it, or if I take this hydrogen out and replace it, I'm going to get the exact same thing as the product. These hydrogens are identical. All I would have to do is flip this molecule over and get the same thing. And I'm hoping you realize that this is also identical. Taking this guy out, I get the same thing. Taking this guy out, I get the same product. These two guys are different, right? So you might say in this molecule there are two types of hydrogens. There's the ones in the corners, and then there's these. Over here, there's one hydrogen that's different from the others. These guys would be equivalent, so there's two types of hydrogens, and 3 over here. Yes, but whatever the answer to the structure is, it only undergoes one monosubstitution reaction product and 3 disubstitution reaction products. Okay, like here, right? Could be a ring of 6, because what I mean by disubstitution, so I'm going to replace 2 of the H's now. So let's say I turn this guy into an F. That's the first guy. F. Now, if I'm going to turn another one of these into an F, like this, That'd be another product. That's one product. If I was to do this guy, it's the same as this one. So there's one product, this and this. Or I could have changed this guy. True? That'd be a second product, where there's a space in between the two F's. This one would be the same as this one. And then I'm hoping you can see that the third product that I could get is if I replaced that guy. So there's three dye substitution products. So it looks like a ring of 6 might be a possibility here. It's very stable, but the problem with this structure is that they never undergo addition reactions. And if I have double bonds like here, here, and here, there's a good chance that I'm going to be able to break one of these and add something in. But oddly enough, benzene, the actual answer to our problem here, never wants to do it. This molecule is very stable. Another problem with this structure right here is that all carbon-to-carbon bond lengths are the same. And that's a problem in this structure, is because the distance from here to here will be different from here to here. The length of a C double bond C is not the same length as a C single bond C. It's a bit of a problem with this, but eventually chemists came upon the correct structure, which is that it's not this structure, which I've redrawn, or by moving the double bonds and single bonds, rotating them all by one carbon. It's not this one and then this one. It's a combination of both at the same time. Resonance structure, like when we were back in Unit 1. So it's a combination. That would account for why all the carbon bonds are the same. It would account for why it never wants to add, because there's no real double bonds if not this or this. It's a combination of both. There's no double bonds. There's no single then double, single then double. It's all they're all equal in strength, not half stronger than the other. So this is what they finally decided on as the structure of benzene. And in the next video, we'll talk a little bit more about it.